So maybe let's start with a quick survey. So who here ran an algorithm or a circuit on a real quantum computer, not just emulator or simulator? All right, give or take half. And this is a school on quantum computing. You are, I would say, among the experts. You are not a typical person in the street, and yet only half of you actually try to run something on a quantum computer. Now, of course, one reason is a boring reason. It's an expensive resource, it's not very available, so most of you maybe don't even have access. But on the other hand, many of you are in universities and you can get some level of access. But the other reality is that it's quite hard to run things on quantum computers. Even for you, experts, not just a random person somewhere, it's quite hard to run things successfully on quantum computers. Imagine that now, every time you write a Python code on your laptop, I'll ask you to take your Python code and write it in assembly, compile it on your computer, and then optimize the performance all the way to the level of transistors. It will be horrible. You'll take your computers, you'll throw it to the garbage, you'll say it's unusable, no human being can use that, right? And in some sense, that's what we expect from people that want to interact today with quantum computers. And big part of what I'm going to tell you about is practicality. I'm going to talk about scientific methods, but we always need to keep in mind that there is a huge difference between a scientific tool to demonstrate that something can work, which is something that scientists in academia, that's many times what we do. We do these hero demonstrations in the lab. We take a very specific problem. We can work for a year to make it work. But that's not practical, right? We hope that quantum computers will not just be a toy for physicists to demonstrate the rules of physics. We want that to be commercially relevant and people will actually execute these algorithms, which means that we need to make sure that the methods that we develop eventually can generalize, that we can run them not on specific cases that we tailored, that we can run them in reasonable time and not taking weeks and months to run a very simple demonstration, and that we can scale. It's a nice thing to demonstrate things on 3 qubits, 4 qubits, 10 qubits, but we need to show that we can run these methods on generic algorithms at larger and larger scales, at least conceptually, and it's hard. We are not at the point that we can run huge algorithms, but at least we need to show that there is some potential to scale. So hopefully I'll convince you that there's still a lot of research that we need to do, and it's a long way, but also I think it's good to be critical and try to understand which of the methods that we see today are more scientific, are more proof of principle. They teach us something on the nature of quantum computers and the physics, and which ones are more scalable and can really transform into technology. So the name of this school is Quantum Error Suppression, Mitigation, and Correction. You mostly heard about correction and mitigation, not much about suppression. And that will be my role. So I'll try to tell you about different methods that belong to this set of tools that go under error suppression. And it's not a coincidence that my talk is around practicality, because what I'll try to convince you is that if we want to think about practicality, the first thing that we need to make sure is that any error that we can get rid of before it even happens, we have to do that, because the other strategies, they have huge cost to reducing errors. We'll have to use them. There is no other way, but there is always an incentive to make sure that when you want to use mitigation or you want to use correction, at least you know that you use the device to the best performance and you don't have anything that is left out there. If you want to cool a room in a hot day, you turn on the air conditioner, but the first thing that you'll do, you'll probably close the window and door, right? You're not going to leave everything open and just turn the air conditioner and hope that some miracle will happen. And the same thing with error suppression. First of all, clean whatever you can, and only then pay this huge price of overhead to go and scale beyond that. So there is no coincidence that I think error suppression and practicality are very strongly tied. And I want to start by first give my definition of what is the difference between suppression, mitigation, and correction. These are 3 different strategies to handle errors. Each one has pros and cons, and you should understand how exactly, what do we get and gain from each one of these methods, but also what is the cost of using one of each method. Then I'll do a review of error suppression, and I say review because it's like doing review of physics. Error suppression is a huge topic. There's a huge portfolio of methods that all can be considered under error suppression. and there is no way I can cover that. I'll just try to give you a taste in some examples. The first one is a very simple one, dynamical decoupling, that maybe many of you know, but what I would like to show you that even though the basic physics is very simple, when you want to scale it to more realistic cases of large algorithms and not just simple experiments or maybe like NMR type of experiments, even these very simple rules start to become quite complicated, and we need to think about practicality. How do we embed dynamical decoupling in a good way when we scale up? And the other thing, I will talk a bit about circuit compilation at an even lower level than what we heard in the last talk, to understand a bit what does it mean to compile circuits at the physical level, what does it mean to compile circuits at the logical level, and when we do these comparisons and we say break even, some code is beyond break even, what do we actually mean by beyond break-even? Typically, that's at the level of one operation. You just, the memory of the qubit is a bit longer or the single operation, but what does it mean at the algorithmic level? I'll show you that in many cases, if we compile on the physical level, we can represent the same algorithm with 3 or 4 orders of magnitude less operations. So if you actually want to outperform that with an error-correcting code, the demand from break-even is much, much higher. So as we move forward and we'll have better and better codes and better demonstration, we'll need to ask these questions. What does it even mean to have a break-even? Eventually, we want to perform algorithms better and not just a single operation better. And finally, if I'll have time, we only have 1.5 hours, so we'll see. I'll talk a bit about near-term applications, and I'll suggest that chemistry and optimization, they have some opportunities, but I'll also try to encourage you to think a bit outside of the box there, because as scientists, we tend to be purists, right? When we think about quantum advantage, we still use the same complexity theory arguments from the 90s around exponential gains. We still think about quantum algorithms as purely quantum. We just run a quantum algorithm from start to end, and that's it. It's either exponential or not exponential. But reality doesn't work like that. Most tools today that people use for optimization are heuristics. Most chemistry pipelines around different simulations of photovoltaics or catalysis, they use a train of many, many methods and approximations that run one after another after another. And the main question that we can ask, can a quantum computer be part of such a pipeline? Maybe a very small part, maybe just 1% of a completely classical part, such that the addition of the quantum computer can actually give us better result than any other pipeline that doesn't include a quantum computer. That will be an example of quantum utility. It doesn't mean that we found an algorithm with an exponential gain, but it means that we can actually use quantum computers even in a noisy sense, and maybe even at the physical level, that can still give us some benefit. And don't understand me wrong, we are going towards error correction. That's the holy grail. We're going to get there, but it's a long journey. It's a long journey that if we think about practical error correction, not demonstration, running algorithms at large scale with error corrections, that can be a long journey. It can be even 2 decades. It doesn't mean that during this time, quantum computers are completely useless at the commercial sense. And something to think about is how to design algorithms that are more fault tolerant. Not just designing devices that are fault tolerant, but designing algorithms that can survive some noise. How can we design pipelines that include classical and quantum such that the classical methods can enjoy and gain something from the quantum insight and give us better results? And that's something that as the next generation, I think is very missing. The quantum computing community is not mature enough in that sense. We still have these canonical algorithms from the 90s, and that's our definition of quantum advantage or not. And there is a lot of room for development around realistic algorithms that can really push and give us some advantage. So I'll try to talk about that as well. All right, so maybe let's start with my definition. I know some people have different definitions of these 3 different strategies for suppressing, mitigating, handling errors on the device. So the first one is error suppression. So error suppression is there's many different methods that fall under error suppression. And what I consider as error suppression is any method that can prevent an error from happening during runtime. Now, according to this definition, you can say fabricating better devices is kind of error suppression. You have longer coherence time, so when you run the algorithm, there is less probability that that will happen. But I'm not going to consider that. I would consider that as an even higher level. Let's assume that I give you a device. It was fabricated already. Maybe it's a good device, maybe it's an amazing device, maybe it's a horrible device, but this device has some limits. The question is, can you run algorithms that really push the device to its limit? And error suppression is trying to do that. We are trying as much as you can to suppress or even prevent errors from happening during runtime. Now, of course, the pro of this method is that one of the pros is that it's zero overhead. You want to include that during runtime. You don't want to include qubits overhead or runtime overhead. You just want to make the execution as faithful as possible. Another advantage, it's a runtime method, which means that you can use it for any algorithm, right? You can use it for a sampling algorithm. You can use it for an algorithm that you want to know some expectation value. You can use it as a subroutine. Many times you'll run something as a subroutine and you'll feed forward the state that you get to some other part of the algorithm. So given that all you do, you just make the execution more faithful, you can use it for any type of algorithm. Of course, the big con of error suppression is that you are still limited by the device performance. So if the device has some T1 limit, has some coherence limit, you won't be able to surpass that. So for that, we have mitigation and correction. So error mitigation, I would define error mitigation as any method that leverages sampling overhead to average out errors. So you accept that errors are going to occur. You are going to run algorithms, and you assume that the data is corrupted, but now you are going to use some overhead in order to wash out these errors and get results that is more accurate. Now, I'll be fair, there are many methods that go under error mitigation, and some of them have different properties. I think yesterday you heard about PEC, probabilistic error cancellation, and many of the things that I'm writing here are quite special to this PEC method, but I can also comment regarding some of the other methods. So if we think about PEC, for example, if you think about what are the pros of this method, so first of all, it can just go beyond device coherence. And the other, that some people will claim that it's not a heuristic, right? You can have some bounds, and then given the bounds, you'll pay some price in overhead, but in general, you can hit your uncertainty bound and calculate expectation value to some limit. But of course, it comes at a huge price. It comes at a price of an exponential overhead. Right? You take a circuit, and then using the noise models that you extract, you create an ensemble of circuits that you run instead of this single circuit, and then you do some post-processing to average. And this ensemble of circuits is typically going to be exponential. So overall, you're going to introduce an exponential runtime. At least for PEC, you need to do detailed characterization. You need a noise model, not of your device, of every layer that you have in the circuit, every unique layer that you have in your circuit. So it's not a coincidence that the recent demonstrations of PEC, the successful ones, used very naive toy models. They use, for example, transverse field Ising model on a line, or transverse field Ising model that is compatible with the device topology, because even though you have many layers, they're very repetitive. So you have like A, B, A, B, A, B. So when it comes to characterization, you just need to characterize two different layers, A and B. But what if you want to run a real algorithm? You want to simulate some real molecule. You want to run some complicated algorithm, tolerant level algorithm. You're going to have millions, if not hundreds of millions of layers, out of them hundreds of thousands, maybe unique layers. It's clearly not practical to characterize 100,000 unique layers and then use these noise models in order to feed it to the method. So you'll have to compromise, right? So you'll have to, for example, assume some noise models. You'll have to maybe characterize one and then translate it to others. But then, of course, you are losing a lot of the promise of these methods. They'll become heuristics again, because your noise learning part is now going to be a complete heuristic, and then all the results will be unbiased compared to your model. But if your model is not accurate, your results are going to be unbiased regarding to something that is initially biased compared to reality. Of course, also another thing, because it's a post-processing method, most of the times it's just applicable to expectation values. So if you want to have a sampling algorithm or you want to have a subroutine, it won't work. And finally, it's a post-processing strategy. Right? And by that, I mean that a single shot, if you take a single sample of your circuit, one of these ensemble of circuits that you want to run, it's not very meaningful. Right? You're going to get a very corrupted state in the end. What is meaningful is that when you take all these corrupted states and you calculate the average of some expectation values over this ensemble. And then what you can show is that in the limit of exponential or infinite overheads, the expectation value converge to the real value. Now, that's, of course, a very legitimate thing to do. But then if we think about error correction, which are runtime methods, it's a big question. Are they compatible? Can you use a post-processing strategy with something that works in runtime? And these are questions that eventually, if we would like ever to combine mitigation and correction, we'll need to answer these questions. Now, I will say that some of these things are not true to all kinds of error mitigation. For example, I think you also discussed yesterday zero-noise extrapolation. For example, in this method, you won't need to do detailed characterization, and you won't have exponential overhead. But the reality is that to date, there is no real convincing evidence that, for example, zero-noise extrapolation is a very successful method. There are just too many moving parts. You'll need to, first of all, use some form of extend the noise in your circuit, whether you'll do it digitally or by pulse level. These are not very exact. And then in the end, you'll need to do some fit, which is quite hard to understand in advance what is the right way to do that. So I would say that all the demonstrations of successful zero-noise extrapolation to date use the fact that they knew what the answer was. And then you can kind of tune the methods to exactly reproduce this answer. But to date, there is no example of a case where we didn't assume anything about the answer that we wanted. We didn't assume anything on the structure. And for example, zero-noise extrapolation at scale, not at the level of 3 or 4 qubits, gave good results. So that's why I am focusing on PEC, because PEC, unlike the other, even though there are big disadvantages here, show that at least at scale of around 100 qubits or so, can produce good results. One last thing around mitigation, you can even think about other methods that maybe quantum mitigation purists will not call them mitigation. But for example, what happens if you just develop a very sophisticated classical statistical methods that can identify outliers and remove them? What if you just run your circuit 10 times with different compilation seeds or with different some considerations, and then again, you use some sort of a sophisticated classical post-processing? Would you call it error mitigation? I would call it error mitigation. Right? I mean, this is not a rigorous error mitigation that uses a noise model, but these are methods that in general can take us beyond device coherence. And I think that as we move to more and more practicality in use cases, developing methods, and that's an open door for you, developing methods that can take us beyond device coherence, but maybe do not require extreme overhead or do not require detailed characterization of every layer in the circuit. That's a huge opportunity, and that's an open research. And I think that we'll see more and more mitigations that are resource-efficient mitigations. All right, the last thing is the holy grail of quantum computing. Most of this winter school was around it, error correction. So in error correction, we are using every possible overhead, qubit overhead, operation overhead, time overhead, but to get the dream scenario, right, where we can detect and correct errors in runtime, right? And of course, the advantages are very clear. It's not limited by device coherence. In general, if your code is good enough and you execute it good enough, you can get as low errors as you want. It's a runtime strategy, right? You correct error as you run the algorithm. You don't do it in post-processing, right? So in general, you can run any type of algorithm that you want. Cons, or huge one, huge overhead, right? You heard yesterday, I think, the talk by Google, which is an absolutely amazing engineering achievement. But let's remember what they showed. The distance 7 code used the whole device, 100 qubits, physical qubits, to realize one single logical qubit, right? One qubit. This is the same thing that is represented by a 2x2 matrix. We can do all the calculations in pen and paper. And it wasn't even an operational qubit. It was a memory qubit, right? So, and I'm not saying that to undermine the result. I just want to impress upon you that This is a very, very hard problem. This huge engineering, this amazing team worked so hard and showed this amazing demonstration that gave us one non-operational qubit that used the whole device. So if we think about going to very large distance codes, and I'll show you that probably we'll need to go to large distance codes because a distant 3 and distant 5 codes are just not going to do that. When we'll ask if they can, at the algorithmic level, give us break even, the answer is probably not. And if we want to go to large distance codes, it's going to be very, very expensive. We'll do that because there is no other way, but we need to be very, very aware of the price that we are paying by introducing these enormous amounts of qubits. And it's fair to say that in the future, when we'll run realistic quantum error correction, 99.9% of the qubits will be devoted to error correction. 99.9% of the operations will be devoted to error correction. 99.9% of the computation time is going to be devoted to error correction. Just a month ago, I was at a talk by IBM. They talked about the gross code. And they show there that a single shot of the gross code took 1 hour. Compare that to 4,000 shots per second that you can do today in physical level. That's a 10 million X. Now, of course, that's a very preliminary demonstration, and that's not necessarily the most efficient code. So I'm not saying that these 10 million will survive. But even if we'll have a 1,000 or a 10,000x in runtime, when we think about practicality, that's a huge factor that we'll need to think. So when we judge codes, we will need eventually to think about these real-life constraints. How many rounds we need to do? How long it takes to do that? Is that even feasible? If we have a 10,000x in runtime, if I take something that can run in 1 minute on the physical level, now it's going to take 10,000 minutes. That's quite a long time. Now, maybe it's worth it, but it really put the bar much higher. We'll need to have very good advantages and huge performance gains in order to justify running something which is 10,000 times more and using so much qubits, which probably is also the reason why we'll need to go to large distance codes, because getting even a 2x improvement may not justify the huge overhead that we are paying. Yes?
What do you mean by not limited by device coherence? Because for error correction, aren't there like threshold theorems?
So I mean that in general, if you can execute any code that you want, you can make it lower and lower. So take just a higher and higher distance codes, just make sure that you are below the threshold. In general, nothing prevents you on the conceptual level to reach 10 to the minus 18 errors. Practicality is a different thing. Let's put it aside. But there is no fundamental limit to the quality that you can get if you have an operational and working error correction, and let's say resources is not an issue, right? Practicality is a huge thing, and of course we are very far from that, and that's what I'm trying to say. So what is the overall conclusion? The overall conclusion is that all these methods eventually, sorry, question?
Yeah, it's like, what is this one shot mean in the BB code?
Oh, so when you have a quantum algorithm, typically, you can think about it in many ways, but typically you can either use it to evaluate some expectation values, you can use it just to create a state, you can measure this state. Typically, if you'll measure this state by some tomography, you'll take many shots, but you can even route this state to a different part of the algorithm. So a single execution, a single run of the circuit, this is what I call shot. Error mitigation, for example, or PC at least, the result that you get after a single run of the circuit are meaningless. The only meaningful thing is that you need to run the ensemble of circuits and average.
Okay. So I guess just like, because the BB code, we are like, what kind of circuit are we talking about here?
Oh, you mean?
1 second.
Oh, that's you mean the one, I mentioned that for the gross code, that's a statement from IBM that they comment last month in the talk. So I just mentioned that to give an impression of what does it mean to in real time to really run, measure all of that, decode, and do all the rounds. That still can take quite a long time and see some net break even. Of course, you can always run it and get results that are much worse than physical level, but that's not the goal. Yeah.
So you have a lot of examples of what you mean by mitigation and correction, but do you have specific examples of what you mean by suppression? Like
yes. So for example, if you can optimize the way that you implement gates at the pulse level, that's an error suppression, right? If you are now 4 nines and not 3 nines, error suppression. I consider compilation as error suppression. If you can represent the same unitary with 10x less gates, and gates are noisy, that's error suppression. I'll talk about dynamical decoupling. If you can remove phase errors and maybe crosstalk in a deterministic way by just including sequences in your circuit, that's error suppression, right? So any method that you can do in runtime and it will prevent the error from happening. Of course, it's a bit of philosophy. If you have much better compilation and you have 10x less gates, sure, you'll have less error. Is that directly you prevented the error? Well, I would say yes. Conceptually, you run the same unitary with much less noisy gates, so you are preventing a lot of the errors that otherwise would happen.
Okay, so you mean more like on the algorithmic, not like device temperature or something like the actual.
That's definitely something that I said that hardware development, I consider that as a higher level. But of course, that's something that we won't escape. We need better devices. That's almost a given. But I always want to think about these 3 methods as I give you a device right now. That's it. You cannot change it. It has the properties that it has. What is the best that you can do? What is the biggest and hardest and most complicated algorithm that you can run with some reasonable accuracy? And use whatever you want. Use suppression, use mitigation, use correction, use them all together. Yeah.
Sorry, this could be a naive question, but what do you mean by runtime strategy? Because don't you always compile a circuit beforehand on the classic computer, then run it?
I mean QPU. So of course you can compile the circuit. That's always true, right? You always compile the circuit, but then once you compile it, you run it one time. In mitigation, you'll need to compile many variants of this circuit, for example, right? And then you'll need to run them all. You need to collect data, and then you post-process this data, and then you get the end result. So that's not a runtime strategy. That's a post-processing strategy. You need to run a lot of samples. Each one separately is not informative. It's only the collection of samples that becomes informative when you do the post-processing. Yeah. All right. So overall, I want to be quite, well, we are all here because we like quantum computing. We're all here because we are very bullish around quantum computing. And I think that I have no doubt that we will eventually get into error correction. And I'm a huge supporter of using mitigation. But what I want to convince you is that if you want to use that or that, the first thing that you need to do, use suppression to the max to make sure that you get the best that you can from the device, and then to take the extra step, this extra mile, and get results that are better than the device coherence, that's where you would like to implement mitigation and correction. The payment that you'll have in this case for overhead will be hopefully better, and there is a lot of room for research of developing more resource-efficient mitigation and correction. I would say that there are many limitations and challenges for error correction and mitigation. I think many of them eventually are related to one word, resources. They are very, very resourceful, and if you've been on Earth in the last 2 weeks and you heard the whole DeepSeek story, resources is a huge thing, right? And this is a huge limitation, and we'll need to find a way to make these methods more resourceful, because right now they are good enough for academic demonstrations. They are good enough for showing specific properties. They are just not good enough to show anything of practicality, and they will be there, but we are not there yet. All right, so I think that's maybe the time to go to the board. So I want to cover some, to give you a taste at least, and not to cover, maybe it's a strong word, some methods that I consider as error suppression. There's a huge list. I think I'll probably just talk about the first 2, because I think there are good examples that show how sometimes very simple rules and simple physics can give you quite a lot, yet many people rarely use them. I would even say that most people that run today things on quantum computers are not even close to getting the results that they can from just using the device quality. Typically, people will see, and I say orders of magnitude lower performance than what the device can give them, just because it's very hard for most of us to implement all these methods, right? So also the ability to automate them and to include them as part of the software stack is crucial, because if you won't do that, people either won't use these methods, or if they'll use them in an extremely non-optimal way. And I'll show that example in the case of dynamical decoupling, which is a very simple from a physics point of view, yet I'll show you that if you use it in a naive way versus a slightly more sophisticated way, you can get orders of magnitude difference in the performance when you scale to large algorithms. All right, so maybe now we can go to the board. All right, perfect. And maybe I'll turn on the light. I think that will be useful. All right, good. All right, so dynamical decoupling. Many of you probably are familiar with that, maybe some not. So I'll try to start very, very basic. Let me know if it's too basic. We can go faster. But I think the emphasis is eventually that I want to show you what does it mean to embed it in quantum circuits. But before we go to quantum circuits, let's really start from the basic. This is truly a one-on-one. So one of the errors that exist in quantum computers are, of course, phase decoherence. And dynamical decoupling is exactly a tool So let's have a very simple model for phase decoherence. Let's assume that you just have a two-level system with some frequency, right? So you will the Hamiltonian for this. I'll use curly H for Hamiltonian because we'll have Hadamard gate soon, so to prevent the confusion. Will just be, in this case, omega naught. I'll leave some room intentionally, sigma z. But the reality is that this thing is going to fluctuate with time because environmental noise are going to change a bit the properties of your system. So you can imagine that there is some noise function, some stochastic function that just exists in this Hamiltonian. So when the qubit is just idle, just sit there, we don't drive it, there are no gates, this is what it's going to experience. And we can even go to a rotating frame, a frame that rotates at the frequency of omega 0, and then the Hamiltonian is just a simple Hamiltonian of that kind. When there is no noise, it's just a zero Hamiltonian. The unitary is just identity, which makes sense. We don't want the qubits to do anything if we don't act on that. But in reality, it is going to experience some evolution. So now let's take a very simple circuit. So let's say we start from the ground state. We act with Hadamard gate, so we prepare an equal superposition. Then we just wait for some time t. And then we do another Hadamard gate, and then we just measure. Right, and let's say we ask what is the probability to be in the state 0. All right, so if everything is perfect, nothing is going to happen during the idling time. Twice Hadamard gates is identity, you're just 100% of the time going to end in the 0 state. But of course, let's assume that now we have some noise, and let's define the overall phase as the integral over this function delta t. And then we can ask now what is the state that we are going to get. So, okay, convince yourself that when you prepare a Hadamard, you just have an equal superposition, but then if we have this Hamiltonian with this total phase, then at this point, before acting with the second Hadamard, we'll just have a superposition of that kind, phi 1 over square root of 2. And now when we'll act again with the Hadamard, because this phi is not 0, we'll just get something that this probability will just become cosine square of, no, let me just write it here, cosine square of phi over 2. Right? Okay. So that's a very simple mechanism, and the question is, can we get rid of that? Now, the true answer is that not necessarily. If this function was a completely white noise, if this function was something with where delta t prime is just a delta function of t prime, there is nothing we can do. Right? There's a completely stochastic noise. There is absolutely no way that if during this idling time. But that's not typically how these kind of noise processes work. These are typically highly correlated functions, so this is typically not a delta function. Of course, as the difference between t and t prime increases, this will go to 0, but these are functions with some temporal correlations. And because they have some temporal correlations, we can even model this phi, which is the integral, as pretty much a random walk. So if we try to plot an instance of this noisy function, phi of t, as a function of t, you'll find that something that looks like a random walk. Now, of course, you can have different realizations. You can have maybe realizations like that, and so on and so forth. And in particular, you can ask, at a given time, capital T, what can we say about this function? So we can probably say that on average, if we'll just kind of run these experiments infinite number of times, it will be 0. But what we can probably also say is that the variance of this function is going to behave in a somewhat diffusive way, right, as a random walk. So this will just be some diffusion constant as a function of t. It will be some diffusion constant, and it will be linear in t. And since phi is a unitless, dimensionless quantity, we can even define it as t over some timescale t phi. All right. So what does that mean? So now let's take. So now let's do some simplification. So we still want to understand whether we can eliminate this noise from this circuit, but let's for a second take a simpler assumption, and let's assume a quasi-static noise. So what is a quasi-static noise? Or if we want the quasi-static limit. So in the quasi-static limit, every time we run this circuit, we have a constant phi, or we have a constant delta, which means that the delta, this function, not phi, the delta during this time is going to be constant, because typically these idling times in circuits are much, much shorter than t phi. However, typically when we want to calculate these quantities, we run these circuits many, many times, let's say 1,000 times, right? And then we average. So the assumption is going to be that every time that we run this circuit, we'll just have a constant delta, which will give us some constant phi. But every time we run the experiment, we can just assume that we randomly sample this phi from a normal distribution around 0 and with a variance, which is, let's say, t over t phi. That's an assumption. So now let's see, what is the average that we are going to calculate if we are just going to do that? We're just going to run 1,000 shots and ask how many times we found our state in the 0 state. So we know that in a given run, the probability that we'll measure 0 is cosine square over 2, but we know that every time that we run it, we have this probability to have a specific value of phi. And now let's say that we do it infinite number of times, so the probability to be in the state 0 is just the integral of cosine square phi over 2 times a normal distribution with t over t phi d phi, right? And I'm not going to do it. Convince yourself it's a very easy Gaussian integral, that this thing is just half 1, let's see, plus e t over twice t phi. Right? So we're just going to see an exponential decay of the probability to find 0 as a function of time. This is the idling time. How much time do we wait? We'll just see an exponential decay with a typical time of t phi. Right? And it will go to half, which means that the quantum information is going to be corrupted in an exponential way because of this effect, because of these small fluctuation. But now we assumed something very strong. We assume that given a single shot, the noise is extremely correlated. We just have a quasi-static limit where we just chose a specific value of this delta, and that's the value of delta throughout the algorithm. So can we get rid of that? And the simple answer is that yes, actually it's very simple to get rid of that. Definitely in this simple model. Maybe we can...
What is T phi again? Sorry.
Oh, so T phi is some time scale. So I just said that there is some diffusion constant, and since it's unitless, I'm just going to denote t to be some typical time scale that exists there.
It's a constant.
It's a constant, yeah, it's a constant. I mean, in practice, that will be the phase decoherence time. So yeah, you have T1, and T2 is typically a function of both. So the T2 that we have on devices are typically, T2 to the minus 1 is typically 1 over twice T1 plus 1 over T phi. So the phase is typically corrupted because of two effects. One of them is this coherent effect, or non-coherent effect, but noise effect, and the other one is just because of energy relaxation that exists. So T1, even if you don't have T phi, just the existence of T1 is also going to lead to some corruption. And what I'm going to say is that we can actually get rid of this guy completely. All right. So for that, let's just use the concept of refocusing or dynamical decoupling, or if you want, DD. So let's do a very, very simple thing. In this circuit now, let's insert some gates. Let's just put an X gate and another X gate and ask what is going to happen. And let's in particular say that this is t over 4, this is t over 2, and this is another t over 4. So we time them in such a way that they exactly occurred at these times. Let's assume for now that all the gates are instantaneous and are perfect. So what we can say in more general is that if we have an operation that can flip the direction of the Hamiltonian, then all we need to do, we need somehow to embed these operations in the circuit. Now, the net effect is identity because x is nothing. So we're not going to change any logical thing. You can just imagine that if you have a compiler and the compiler doesn't know, it will just make these two gates go away. But let's say that we have that. So what can we say about this function? So effectively, it means that here we have this function delta. And remember, it is fixed in the quasi-static limit. During this evolution, we have minus delta because we just take the Hamiltonian, which is just a sigma z, and we just sandwich that with two X gates from both sides. And then we have another delta here. So if we think about what is the total phase that we are gathering, so we are gathering some phase with an unknown delta. We don't know what delta is, so it's some rate. But then after t over 4, we flip the direction, and now we are going to some minus value. But then at 3t over 4, we again flip the direction such that in this quasi-limit, we are exactly back at 0. Like nothing happened. So this phase is non-existent. Now, of course, every time we run this experiment, we'll have a completely different value of delta. So the slopes will be different, but the same thing will be true. Right? Every time we run it, we are going to end with 0 phase. Now, of course, you can say, well, the quasi-static limit is maybe not great. Sure. So if this is just too long, if this idling period is just too long you can always do, let's say, 4 X gates, right? So just, make for simplicity, I'm just going to use now instead of writing X, I'm just going to put lines, right? You can have a train of many, many X's such that the overall temporal variation that you have in the noise in these timescales is negligible. So at best, you can suppress the errors quite a while. Now, of course, this is a very, very, very simple and naive way to do dynamical decoupling. And actually, there's a huge research from the 50s around NMR of using very sophisticated pole structures. I mean, here I used a very simple sequence, just XX. It's a very naive sequence. But the point is that what I want to show you is that even if we just take this very, very, very naive sequence of just XX, when we'll go to circuits, it is still good enough and complicated enough to pretty much cancel most of the errors that we see if we are aware of the time scales and we know how to find their times very accurately. Yes?
Yeah, I'm sorry. Where is the assumption of color noise coming into this? Because how would the distribution be different if it was a white noise?
Yeah, so I mean, here I assumed completely quasi-static noise, but if that was a completely white noise, it will be harder to show that this is actually linear. So I'm not doing the exact math, but otherwise it will be quite hard to show that it's exactly linear. But the point is that for that, it's actually not crucial. But what would be crucial is that the assumption that we had here will be completely irrelevant, because imagine that right now, the value of delta has no correlation, no matter what the small time scales that you have. It's a completely random. Let's imagine the delta is a completely function like that, and now you put an X gate here, and you put an X gate here. There is absolutely no reason to believe that if I take the contribution here and here minus the contribution here, you'll get something that is better than just the overall contribution, right? You'll just get that it's the same. It probably won't hurt you, but it also won't help you. So you can always think about phi 1, phi 2, and here, if you want, let's call it, or maybe phi 2 and phi 3. So here, in the quasi-static limit, we know exactly that phi 1 plus phi 3 are minus phi 2. If you relax the quasi-static, but you still have strong correlation, that will become something like that. But if you just have completely white noise, that will just be whatever it is. Yes. Yes.
So I see that in experiments, people use XY4 and XY8.
Yeah.
So what's the role of the Y gates then in this case?
So it really depends on and so I took here a very naive Hamiltonian. So you can describe it and also try to account for other terms and other rotations that can happen there. So there's actually a huge research. You can even have sequences sometimes with 8 and 12 and so on gates. And actually in the context of NMR is many times quite important. You have very long idling times. But what I want to show is that when we think about quantum circuits, it's more about the number of idling periods. I'll show you that on, for example, fixed connectivity devices. Most of the qubits, most of the time, are idle. We are so obsessed with gate errors, but in reality, most of the errors come to the circuits when qubits are just sit there idle, because 90% of the time, they just sit there idle. But if you look at a specific idling period in the circuit, these are typically way shorter than the typical decoherence time. So it's the aggregated effect of having thousands and tens of thousands of idling periods, but within each idling period, typically it's short enough and the noise model is simple enough that even a very simple X or maybe XY, if you know something about the noise structure, can be quite helpful. Typically you won't need to go to very complicated, but that's an independent and valid research. You can always try and find better and better motifs to try and improve that. But I actually want to focus on how we embed these motifs and not necessarily how do we choose the best motifs. All right.
So this sort of assumes that the presence of this X thing assumes that nothing's happening along the bit flip channel, right? So it's only the phase error that you are looking at. So you're sort of you're using the fact that your circuit has perfect behavior with respect to bit flips versus phase flips. What if not?
Of course. I mean, bit flip and T1 effects are going to corrupt the information as well. And eventually, error suppression cannot handle everything. But I'll show you that this noise channel is something that we can eliminate. We'll still be left with T1. So actually, what I wrote here is that the overall effect, the decoherence of the phase, has two contributions. One that comes from, if you want, bit flip or energy decay, and one that comes from this, I would say, more coherence phase. We can eliminate that. We won't be able to eliminate that component. So that will still be there.
Because here you could do something even worse. I mean, you could follow your first Hadamard by an immediate Hadamard with very short time and leave it doing nothing, and then do another Hadamard. You have two Hadamard scans though, right?
No, of course. I mean, this is a stupid experiment, right? This is an identity. I intentionally use this as a demonstration.
But imagine instead of X, you use 8. It could do even better.
I mean, oh, you mean here if I'll use H? Maybe in this example, but in reality, you don't really know what is the state, right? You run a circuit, you have a very complicated circuit, and during this circuit, you are going to have some idling periods, and you don't really know what is the state that you have in this idling period. So that's why typically the way that you design the sequences is just by what is the noise Hamiltonian that you have, and in this case, I agree. For Z, you can use also H, right? Sure, you can use Y, right? You can use X, Y, Y, X. You can use many different sequences. It's absolutely not unique. intentionally, I want to keep it as simple as possible to show that even with this very, very simple rule, when we'll try to complicate things to circuits, it starts to be complicated. But absolutely, there is probably a 60 or 70 years research around sequences of dynamical decoupling. So this is not something that is simple, and I completely agree. All right. But now the question is, can we do better than just dealing with this type of noise? And the answer is that, yes, dynamical decoupling can do more than just that. So let's take a slightly more complicated case. Let's assume that now on top of decoherence, of phase decoherence, we have another thing. Actually, I think these move. Oh, is there a board here? Okay. Let's try to use that one. So let's take another thing that can happen in quantum devices, and this is crosstalk. These boards are not for short people. All right. So what is crosstalk? So crosstalk is an effect that two qubits interact in a parasitic or unpredicted way. Right, so one very, very simple example. I'm not going to do the math, but actually it's a nice exercise. Assume that you have, let's say, two transmons, two superconducting qubits, each one with some frequency, omega 1 and omega 2, and maybe unharmonicity, 1 and alpha 2. And let's say they are coupled with some coupling G. Now, typically, if this coupler is tunable, maybe you can turn it to 0, or maybe make it very, very small. But even in fixed frequency qubits, this is still very, very small. So typically, G is much smaller than the difference in energy. And that's good, right? Because if it wasn't like that, then even if you just leave these qubits as they are going to interact and evolve quite strongly. But convince yourself that even in this limit, even though you cannot really have a real processes where, if you want kind of a state go from one qubit to another because it will violate the energy, you can still have processes you can do perturbation theory where you have, let's say, some virtual process where something jump back and forth. And convince yourself that if you do a second order perturbation theory and you ask what is the Hamiltonian that describes these two qubits, so of course the Hamiltonian that describes these qubits will be something like omega 1 Z1, omega 2 Z2. I project to the first two levels, so let's ignore now all the other levels of the transmon. So of course this will just be what you would expect if you just had two transmons, but then effectively you are going to have some ZZ term. Now, you don't really want this ZZ term to be there because you want that if you don't act on these qubits, you don't want them to evolve. You definitely don't want them to develop entanglement between them. You want to control entanglement. You want that only entanglement will happen when you act with a C0 or a CZ. You don't want them to develop entanglement when they're idle. So let's assume that this is what we have on superconducting qubits, and let's take this simple experiment and just run it on two qubits that are next to each other. So we do Hadamard gate. We are waiting for some time t, another Hadamard gate, and measuring, but now we'll have another qubit, so we'll do that on the nearby qubit. Right. And now let's do the same trick that we did before. Let's put x gates at t equal 4 and 3t equal 4. So what is going to happen to this Hamiltonian? So when we act with these x gates, so during this middle period, these terms are going to flip sign, but this term not. Because if we act simultaneously with two x gates, so xx, zz, xx is just zz, right? Because this commute with that, and then the x's will kill each other, right? So it means that if we'll just run it, we are going to get now, again, that the probability to find the state back in the 0-0 state, which is what we want, is again going to have some cosine, but now it will be a different phase. It will be phi zz, which in this case is not even noise. It will somehow depend on this quantity that can be very, very different between different pairs. But that's a horrible type of error, because if we think about error correction, this is a coherent error. This is something that is completely going to destroy all the assumptions that we have when we act with error corrections, that errors are not correlated, that we're just developing here entanglement and correlations between the qubits during idling periods. So that's horrible. So we definitely need to get rid of that. Now, in this simple case, actually, it's quite easy to do that, right? So let's do the following very silly trick. And the first thing is the understanding that here we chose 1/4 and 3/4, but actually that was quite arbitrary. All we really want is that the time between these x gates will be equal to the sum of the parts outside of these x gates, right? Because then we'll have this overall phenomena that we evolve for half of the time with one slope and half of the time for the other slope. So maybe for the second qubit, let's move it just to 0 and t/2. So individually, each qubit is going to handle the single qubit, because this now will be, in terms of single qubits, plus, minus, plus, and this it will be, let's say, I don't know, minus and plus. But if we think about the ZZ component, so now every time we act with a single x gate, we are going to flip it. So we are going to flip it, flip it, flip it, flip it, and overall, we are going to cancel that, right? Okay, so for example, when you just do that, you can get rid of both the single qubit, and in this case, the ZZ. Now, in general, ZZ is a specific type of crosstalk that exists in superconducting qubits, but you can have other kinds of crosstalks that exist in other systems. For example, in ions, many times you have an XX whenever you drive a qubit, so other nearby qubits can fill XX. ZX is something that exists, for example, in spin qubits. You can have even more complicated, but let's say that I give you the structure of the crosstalk. You can, in general, try to design something that will cancel that. And the important thing is that you need to know what are the types of noise, but you actually don't really need to know these coefficients. You don't really need to characterize what are these delta that we had in the single qubits or what are these deltas that we have here. It's actually, if you have a device with many pairs, this term is likely to be very, very different for different pairs. But you don't care, because you don't care about the value, you just care about the fact that it is static during the operation, and this property, this correlation, temporal correlation, is what allows you to get rid of that. So now, let me show you some results, and then we can even do a bit more complication. All right, so I'll take down that. All right. So first of all, okay, perfect. Let's show that this thing is actually can work. So you can run this very, very simple experiment. Just Hadamard on all qubits, then waiting some time, and Hadamard on all qubits. That was too much. All right, perfect. And let's compare three things. Not doing dynamical decoupling at all. Doing a trivial dynamical decoupling where you just put on all qubits at 1/4 and 3/4, and a staggered dynamical decoupling. And you can measure the probability to be at 0. Ideally, of course, you want everything to be flat at 1, because these are idling, nothing should change. But you can see that you can actually get much, much better performance that in this case is just limited by the T1. So you're not going to get a flat line. It is going to decay, but you're eliminating this very extreme noise that exists on these devices just by using this simple thing. Now, you can say in this case, well, that was a trivial example, right? We just took 2 qubits. They were mutually idle. We did it with pen and paper. That was really trivial. Now, reality is a bit more complicated, right? In reality, delays in quantum circuits are not commensurate. They don't ask us where to come. They don't start together. Sometimes when we have an idling, it is in parallel to a gate. Sometimes it's in parallel to other idling. There are sometimes connectivities that many qubits are all together coupled, and the idling is going to affect each other. And actually, even this circuit is very, very simple. In reality, you are not going to have 7 or 8 idling periods. You're going to have thousands of idling periods in a circuit. And the question is, can we somehow embed these simple sequences? And when I say embed, we have 2 X gates. We just need to say, where do we want to put them? We need to time them. Do we want to put them at 0 at t/2? Do we want to put them at some arbitrary time and another time? How can we embed them? How can we decorate the circuit? And this is an example. We get an input circuit. We return a decorated circuit, where here each green one is an X gate. So from a unitary point of view, it's exactly the same, because all these green ones amounts to identity. They never do anything beyond that. By the way, this is a terrible embedding because you can see that you have here sequences of many, many, many X gates, and in reality, X gates are not zero time. X gates are not perfect, so having this series of a lot of X gates is actually not a good idea. They're also going to hit the device probably if you're just going to have crazy sequences. So you can define an optimization problem and ask, I get some circuit. I want to embed dynamical decoupling such that, first of all, I have minimal number of dynamical decoupling gates. Because gates, even single qubit gates, they have some error, they have some finite duration. But you also want to make sure that by the completion, you completely cancel both the both the single qubit and the crosstalk that you have given some crosstalk Hamiltonian. And you want to do it not at the scale of 6 qubits and this very, very small circuit. You want to do it on circuits with hundreds of qubits and with millions of idling periods. How do you do that? So we wrote a paper that suggests the following thing. So first of all, it's not enough just to have the circuit. You need to have the device connectivity, because you need to understand which qubits are going to experience some crosstalk and which qubits are not going to experience some crosstalk. Actually, this is a completely imaginary device connectivity. We demonstrated on different lattices like the IBM Heavy X and square lattices and so on. And you can even do more and more connectivity. But let's say that you just have that. So now what you do, you generate a different graph, which we call it a dynamical decoupling or the delay graph or the idling graph, where it's very, very simple. Each element, each node in this graph is a delay. So when we'll go to very big graphs, we'll have millions of nodes here. And we'll have an edge between two delays if and only if they have some overlap both in time and in real space. So in real space, it means that in this case, qubit 1 and qubit 3, they have an edge. So I can go and see between qubit 1 and qubit 3, are there some delays that overlap? Yes, delay 3 and delay 5, they have some temporal overlap, which means that delay 3 and delay 5 indeed should have an edge between them. So eventually you just create this graph that just tells you what you should do. And then what we showed in this paper that we can actually develop a graph traversal algorithm, extremely efficient one, that just go one by one and analytically find the exact timing of the X gates that you need to have. And in each one, you do it according to the parent nodes in such a way that the overall embedded circuit that you have completely and exactly, and at least in simulations, we can show that this is exactly, but I'll also show you real device data. We can completely cancel all the crosstalk and all the dephasing, at least within some assumption on the typical phi, assuming that these idling periods are still relatively much smaller than. So let's see some demonstrations and results. And also, we talked about practicality, so I need to show you how practical is it to do that. So, of course, you can test it on all kinds of algorithms. We have a lot of algorithms. I just choose here quantum Fourier transform and Bernstein-Vizorani because they're very different structure. Bernstein-Vizorani is a very simple algorithm, but it has huge idling periods, and quantum Fourier transform is a very canonical one. And here, I'm not comparing with and without error suppression. I'm comparing two identical circuits. Everything is identical. I'm not even comparing it versus no dynamical decoupling at all. I just compare trivial dynamical decoupling, where you go to each idling, and you just put X gate and X gate at 1/4 and 3/4. And I compare it with the graph-based method, where we choose that. And this is a logarithmic scale, and this is circuit fidelity. By the way, if I'll put here also no dynamical decoupling at all, you won't even see it. At the level of 12 qubits QFT or 30 qubits BV, no dynamical decoupling will just give you 0 fidelity. I mean, the circuit is going to be completely corrupted. But you can see that here on this logarithmic scale, you can still get 2 orders of magnitude difference just by embedding dynamical decoupling in a slightly better way. Yes?
So just a small question over there. So this is crosstalk during idling, but what if you have the crosstalk while at gate application?
Absolutely. So you need to characterize that, and this is something that we do take into account. So there are a lot of context, and this is all under contextual dynamical decoupling, right? There are infinite context, right? You can have both idle. You can have one is idle, and during the idling, some other qubits now become driven. You can have, if you have 3 neighbors, maybe some are idle and some not. I mean, we can go and number all the different scenarios that can happen, but we account for that. So
the edges on the graph are not just both idling together.
Yes. So you can add more richness, and then you'll have slightly more complicated graphs where the graph also tells you which kind of overlap do you have. But what I also want to show is we should also ask, what is the time? Okay, so I described some procedure. And you can see that if I compare the time that you need in order to embed, in order to create this decorated circuit, it actually scales linearly, and it's pretty much the same as the standard one, because it's a simple graph traversal, right? The standard one will just go idling by idling, so you also need to traverse, and just put at 1/4 and 3/4, it's a very trivial one. You can see that actually the graph traversal is exactly the same, and if you ask in terms of practicality, when we go, for example, when we embed in a 100-qubit quantum Fourier transform, there are about 6,000 idling periods, and we do it in about 3 seconds. Right? So it's about 1 second per 3,000 idling periods, and this is done on Python on a laptop. We actually now have a Rust version of that on multiple. We can do pretty much 3 to 4 million idlings in a second. That's not a bottleneck. So even now, if you've given me an algorithm with 100 million, it will take us a few seconds to do that. This is absolutely not a bottleneck to do that. And these are for algorithms, but eventually we would like to run error correction. But error corrections are just algorithms, right? We need to do syndrome checks. We need to prepare the embedding. We need to do the corrections. We need to act with the specific logical operations. Each one of them is a quantum circuit, and these quantum circuits will must have all these suppressions in them, because otherwise the amount of noise that you let these processes put into your circuit will just overwhelm the quantum error correction, and will just require you to handle all this using this huge overhead. So these tools are also nice in now when we run things on the physical level, but definitely if you want to run an error mitigation, it makes sense to use that, because you just lower the bar. You need less overhead because your starting results are better. You get rid of a lot of noise mechanisms. When you want to run syndrome detections and corrections, you need to use this, because that is going to prevent these coherent errors that are so catastrophic. All right, so that was dynamical decoupling. It was just one example of how smart design can really push you towards the system performance, or what the device can give you. By the way, I said at the beginning that today when people run algorithms at scale, 50 algorithms, or 50 qubits, or even 20 qubits for the quantum Fourier transform, they see orders of magnitude lower performance than what the device can give them. Here I showed you 2 orders of magnitude, but this is not even the full suite of error suppression. Here we just compare 2 versions of the same concept, dynamical decoupling. We just compare dynamical decoupling, like simple dynamical decoupling, and context-dependent dynamical decoupling. And that alone gave us 100x difference in performance. So imagine what does it mean to actually run a circuit in a bare way without even introducing dynamical decoupling, without compiling, without doing gate optimization, without optimizing all the things there. People just see absolutely noise in cases where they can actually get quite good performance even with today's devices. So that's something to keep in mind. All right, any question on dynamical decoupling before we move on? Oh my, we are going slow, yeah.
So the time you show, that's for doing this compilation.
Yeah. This is for the classical processing where you embed. In some sense, you can think that you have this process that you get as an input a circuit, and you return. It's part of your compilation, if you want. You return a decorate. How long it's going to take you? If that's going to take you 2 weeks to find the optimal embedding, well, great. It's a great academic paper. You can publish to show that you can find that, but that's not practical. No one is going to wait a week for you to embed the dynamical decoupling, right? All right, so I want to talk now about compilation, and I want to talk about compilation in a slightly lower level. And actually, this is a huge topic with great groups, including here, a Jason group in UCLA, one of the best in the world. So I'm just going to give you a very, very, very mild taste of the complexity and the importance of quantum compilation. So it's definitely not going to be a comprehensive discussion around that, but definitely people here in UCLA, you have resources to some of the best groups around that, so I'm sure you can fill the gap. So before we talk about designing compiler, we need to understand that compilation is going to be very, very different for different systems. Right? So we can think about low connectivity and static devices. These are typically the solid-state systems, superconducting devices, spin devices, and this is just an example for the current heavy EXCO devices, but IBM are going to develop new devices with better connectivity. But no matter what, it will always be relatively sparse compared to the full all-to-all connectivities, right? Even if they'll have 6 or 7, it will still be limited. Now, of course, the huge advantage is that operations are extremely fast. Right? So you can do operations very, very fast, and that can somehow compensate for the fact that connectivity is limited. Other devices, for example, like ion chains, they're still static. So in an ion chain, the ions are static. They don't move. But on the other hand, because interaction is mitigated by motional modes, you can do non-local operations. So you can, for example, do a direct gate between two ions that are far away. But that, of course, has its own cost, right? Doing ion chains and scaling them is extremely, extremely challenging. And other devices, on the other hand, they have a dynamic approach. And that's true both for ions. For example, for those of you who are familiar with Quantinuum, the QCCD approach, where you pretty much have few interaction zones. So gate can only happen in these interaction zones. And most of the time, qubits sit somewhere on the bench and waiting for their turn to play in the circuit. And every time a qubit turn comes, you shuttle it to one of the interaction zones, and then you just act on it there, right? So on one hand, it's all-to-all, right, because you can just move them. But on the other hand, this shuttling is very, very time-consuming. I think in a recent, or maybe it's already a year and a half ago, paper by Quantinuum, they show that about 99.98% of the computation time is shuttling. And all the rest is reset, measuring, doing all the single qubit gate, two qubit gates. So 99.98% of the computation time goes to shuttle the atoms. And you need to do it slowly, because if you do it fast, you'll have decoherence, you're going to lose the quantum state. So, and that's true also for atoms, right? So definitely for the demonstrations that we have right now, we can overcome that, because we design experiments that don't require too much densing, I call it, right? You want to prepare like a G8Z state or something like that, so you can do relatively some global shifts, or maybe still very hard and impressive. But as we'll go to more generic algorithms where you have many, many unique layers, and each unique layer includes interaction between very specific qubits, doing this very complicated motion of all the atoms is going to be very, very challenging. And it still can get better and faster, but all I want to say is that there's no direct winner here. Each one of these platforms, it has its pros and cons, and it really depends on the use case and algorithm and our ability to actually push these to show whether which one is better. And in all of them, compilers are going to be crucial. Whether you want to compile here the way that you design your circuits to minimize the need to do this very expensive, time-expensive shuttling, or whether you want to compile it here to make sure that you don't have too many gates and too long circuits because of the low connectivity. All right, so let's go back to the board now. Okay, I'm very short in time, but let's just go and stop me whenever it makes sense. All right, so the first basic thing that all gate-based computing rely on is the notion of universal gate set, right? The fact that we don't need many gates in order to realize any unitary, right? And in particular, when we think about hardware, there is another notion, and this is the notion of a native gate set, which native gate set are the type of gates that you can implement at the physical level on your device. And of course, we want that the native gate will be at least a minimal universal gate. Ideally, maybe you want it even to be better than that. And let's take some examples and see why this is actually crucial, and why sometimes the freedom and the richness that we have at the physical level can give us a huge advantage, and why when we think about quantum error correcting codes, for example, what is a native gate set can be quite an important question. So let's first start from some simple examples. So let's start with single qubit gates, first of all. So most hardware providers, they don't give you as a native gate every possible single qubit gate. You only have a very specific type of gates, because every time that you have a gate, you need to calibrate that, right? You want these gates to be 4/9 fidelity. There is a limit of how much time you want to spend for calibration. Remember, these are eventually going to be commercial devices. You don't want your device to spend 14 hours a day for calibration. You want maybe to spend 10 minutes for calibrations and to leave the rest of the 23 hours and 50 minutes for users to run things on this machine. So many of the providers, they have typically a single basic gate. Typically, it's some 90 degrees rotation, either Hadamard or some, for example, a 90 degrees rotation around the X gate. And on top of that, there is typically one parametric gate, which is typically an arbitrary angle rotation around Z. And the reason that it's very easy to have an arbitrary rotation around Z is because these gates are typically virtual. What it means is that you just define them in software. Right? This is not a real pulse that is going to change the state of the qubit. You just change your frame. Right? What is a Z rotation? You just change the way that you define the X and Y. So these gates are free. Right? They have no noise. They are zero time, so you can use them as you want. The point is that there is only one such rotation. So typically, the Z rotation is the one that we can choose to be virtual. I mean, of course, what is Z, X, and Y is completely arbitrary. So typically, the one that we choose to be virtual, we call it Z. And then we just want to have another implementation of a 90 degrees rotation. And this will be an actual physical implementation. So it will be like with either laser, if it's ions, or with some microwave pulse, if it's superconducting qubits. It will actually be some implementation which is going to have some error. Now, of course, we want to create arbitrary unitary, but luckily we can, an arbitrary unitary for a single qubit is just an SU2 matrix. So there are many ways to parameterize that. So for example, one way to parameterize that is what is known as the U3 decomposition, which is just a cosine of theta over 2. Cosine of theta over 2. We'll have sine theta over 2, and now we'll have here, I'll write it down. That will be minus lambda. There's a minus here, and sinus of theta over 2, and yeah, e to the I phi. Right, so convince yourself that every single qubit unitary can be written in terms of that. And the nice thing is that with these two gates, it's enough to represent each such gate. So for example, I can show you that every gate, and okay, up to a global phase. So if we'll have RZ of phi plus pi, I'll denote that just for brevity as square root of x, just as a notation. It's a 90 degrees rotation, so twice this gate is x. So that will be square root of x. It will be another RZ of theta over pi, another square root of x, and finally RZ of lambda. Right? So if we don't mind using two such gates and whatever, all the free RZ that we have, we can generate any single qubit unitary. In particular, for example, if you want an arbitrary Rx rotation and not just pi over 2, that's fine. That will just be, for example, this U with some arbitrary theta and minus pi over 2 and pi over 2. Right? And this will just be an arbitrary Rx rotation around theta. Of course, the price that we need to pay is that now if we want an arbitrary rotation around x, we need to have two such gates. And remember, these gates, they have some error, they have some time, so ideally it's less favorable. Now, of course, if you have a native Rx theta, it can be very helpful. And this is something that, for example, exists in ions, and these days even IBM. So you do have a pulse level definition that can give you natively an Rx of theta. Now, of course, that's a huge challenge because you need to make sure that all these gates are very high quality, right? And even when you choose a different theta, you can still maintain the 4 nines or 5 nines fidelity that you want for single qubit gates. But when it comes to compilation, it means that having this slightly richer gate set, you don't need it for universality. That's more than enough, right? A Hadamard gate or a single RX90 is enough for universal gate set. But having the richness is extremely important because when you compile the circuits, you just get much, much better representations of your unitary in terms of your gates. And the same thing is true if we go to 2-qubit operations. So for 2-qubit operations, remember that for universal computation, we just need a single perfect entangler. And notice that we need a perfect single entangler. So let's say that we have some device with a bunch of qubits, kind of arbitrary plotted. So we don't even need to have a perfect entangler between any 2 qubits. We just need to have a communication path that go between any 2 qubits. So if we just have a perfect entangler between these qubits, this qubit, there is a direct communication path between, in this case, any 2 qubits. So that's enough. So for example, for universality, it's enough to have a one perfect entangler, for example, a CZ implemented on any of these edges. And different systems are going to have different native gates. So for example, there is the C naught or CZ and RXX or pi over 2 rotation, 90 degrees rotation. These are all equivalent gates. They're all equivalent in the sense that all these 2-qubit gates are similar up to single qubit rotation. So they all belong to the same family, and typically you'll have one of these for many of the devices. It doesn't make much sense to have both of them because you can just move between them with single qubit gates, but you also have other families that are not equivalent, for example, the I-swap gate. Which is a different one. So for example, it makes sense to have maybe both CZ and I-swap, because what we know is that any 2-qubit unitary can be written with up to 3 perfect entanglers. It doesn't mean that any unitary can be written in terms of entanglers. Sometimes if you have I-swap, you can just compile it or synthesize that in a better way. Even more than that, these are just fixed angle, but imagine that now you'll have an arbitrary RXX or RZZ rotation. So even if we just have C naught, for example, an arbitrary ZZ rotation can be written in terms of 2 C naught. So you just do a C naught, you do a simple RZ rotation of angle theta, and you do another C naught. This is actually a realization of a ZZ gate with an arbitrary rotation. But imagine that you have a native implementation. So instead of using 2 C naughts, you just use 1. So less duration, less error, that's good. And this is something that many times people don't realize, that when we compile things, and by the way, this is, for example, gates that are now available on IBM. Or if we think about like ions, the Momer-Somerson gate, the MS gate is an arbitrary XX rotation. So these things exist. And typically when we think about error correction and codes, they're typically, because of the complexity, it's very limited. And when we compare, how do we evaluate 2 algorithms, one on the physical level, one on the error correcting level, sometimes we are comparing apples to oranges. Because when we compile a circuit, a semi-unitary, with the rich physical gate set, we can sometimes, and definitely at large scale, at algorithms with billions of gates, we can sometimes get 2, if not 3 or 4 orders of magnitude overall less gates when we compile them on the physical level. So then when we ask, are we beyond break-even? We need to maybe ask, what do we mean by being beyond break-even? If I can run the same algorithm where each operation is twice as good, but I have 10 to the 4 less operations, what am I going to prefer? And I don't have an answer, actually. It's just some of the things that when we think about codes, it's good to think about. Maybe it's too early to think about it, I'm not sure, but it's definitely something that at some point we'll have to think about. Now, I stopped here at, okay, so maybe one thing to say about 2-qubit rotations. So one thing that we can use is the CAC decomposition and the fact that any SU4 matrix, any 2-qubit rotation, have a very simple form. We can write it as some single qubit operations, K1 and K2, and then just, I'll call it XX, by it's XX rotation with some angle A, YY with some angle B, and ZZ with some angle C, and then another single qubit rotations, Q3, K3, and K4, and this is known as the CAC decomposition, or if these are the Cartan or defines the wild chamber. These are the canonical operations that define the nature of the 2-qubit, and using this very well-known decomposition just tells you that if I give you a gate set, it may be universal, it may be even more than that, and I give you an arbitrary unitary, there is a very easy way to synthesize that. That's actually a solved problem. It's very optimal. You can always do it very, very straightforwardly. You don't need to think about that. Now, you can ask, what happens if we go to higher number of qubits, right? So, of course, if you have 3 qubits, you can say, well, sure, I can always break it to 2-qubit operations. Let's say I have 3 qubits, I have some unitary, so maybe I'll have some operation here. This line is an arbitrary one, not necessarily a specific famous gate. You can have that, maybe 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 you can have that, and so on. And now you can say, all right, I can write it in that way. I know that each one of these I can write with up to, at most, let's say 3 C0. Great. But that doesn't answer the question, can you somehow decompose this full thing, not in terms of bunch of 2-qubit operations, can you directly decompose it? And the answer is actually, yes, you can show, okay, it's hard to show, but any 3-qubit unitary can be written with up to 14 C0s or CZs, and many times doing the decomposition at higher level makes sense, because if you just break it to blocks of 2 qubits, you are left with maybe quite a lot of gates. And of course, you can go to 4 and 5 qubits, but there is a huge price for that. First of all, many of these analytic and nice results are not applied at higher, so you need to run some optimization, and in reality, you may find some things that are not great. And the other thing is that it can be quite resourceful. And I don't think I'll have time to talk too much about routing, but then when you want to also do the next step of compilation, of routing, it will have some cost. So it's a computational cost, and eventually it's a trade-off. And compilation is a world of trade-offs. You can do very exact and optimal compilations, but it may take you forever. You can use very, very fast heuristics. It will just give you very poor results. And the question is, how do you balance these two things and find the thing that is best for you, given the considerations that you have? Maybe compiling a circuit for a week, it's not relevant. But on the other hand, maybe if you just compile it in 1 second, it's such a poor result that there is no chance it can run on today's computer. So how do you find the right balance between having a circuit that can run on today's computer, but on the other hand, maybe it's not, you don't need like 7 hours to compile it. All right. So let's see. So, okay, so maybe I can take just, maybe I can just jump to some results. So I wanted to tell you also about the next step, which is routing, and explain why routing is a very important step, because eventually what you can do, when you have a circuit, you can always consolidate, let's say create blocks of 2 qubits. And what you know is that as long as the 2 qubits are next to each other, that's not a problem. You can just take your basis, the native gate set, and use, for example, this CAC decomposition and what I showed you to write it. But what happens if your qubits are not next to each other, right? So before you do that, you need to solve the routing problem, and to make sure that every time that you have a 2-qubit operation in your system, it's always defined between 2 qubits. And in order to do that, you'll need to insert swaps. And I wanted to define a bit this problem and kind of show you why, in general, solving it exactly is an NP-hard problem. I don't think we'll have time to do that. So I'll just show you some results just to show you how important and how crucial just different compilation schemes can be. And I think with that, probably we'll finish.
That's all right.
Oh, okay, fine. So I have time. All right. Okay. So maybe if I have some time, maybe I can quickly just define the problem of routing. I'll just define it. So let's say, first of all, I give you a circuit. Right? So the first thing that we typically want to do in the circuit, and completely logical, I don't care if I have these operations or not. So let's say I have some circuit, and I have a bunch of operations, some 2-qubit gates, some single-qubit gates. So, okay, it's a very silly circuit, but never mind. So the first thing that we typically want to do, we want to consolidate. What does that mean? I want to group these 2 blocks of 2 qubits. Okay, in this case, it's a kind of a simple one, where no other qubits are involved during this block. Let me do it a bit in a slightly less trivial way, maybe. So in this case, we'll have these 3 blocks, for example. Right, okay, and let's say here we had some 2-qubit operations between these qubits. Right, so eventually, once you consolidate that, so you just have, and each one is a unitary matrix, right? It's a 4x4 unitary matrix. You just take all the gates here, you multiply them, and so what you eventually have, if you kind of coarse grain, you just have a circuit with a bunch of matrices, 2 unitaries that in this case act between these 2 qubits, between these 2 qubits, and let's say between these 2 qubits, right? So before you even write these unitary matrices in terms of native gates, you want to make sure that they are next to each other. So how can we do that? So let's take a simple example. Let's say that we just have a device that has 3 qubits. This we'll call it Q0, Q1, and Q2. And let's say that we have a circuit of that form. So let's say where we have some 2-qubit operation, and then we have, let's say, another 2-qubit operation, and then finally we have another 2-qubit operation. Right? So now we need to assign each physical qubit. So let's say that the physical qubits, we'll call them P0, P1, and P2. We need to assign physical qubits to logical qubits. So first of all, we see that the first operation that we have is between P0 and P1, so okay. And then the second operation is between P1 and P0, so maybe it makes sense to actually say that, yes, this will be P1, this will be P0, and this will be P2. So you can see that in the first layer, it's easy. The 2 qubits are next to each other, so we can just go, use the synthesis rules that I showed you to write it in terms of your basis gates, great. Now we go to the second layer of the circuit. Great, it's also existent. We have it here. So we can just do the same thing. But now we go to the third one, and all right, now P0 and P1 are not next to each other, so we'll need to insert a swap. So for example, we can insert a swap gate here. And what the swap gate is going to do is just going, let's say, for example, to flip P2. And actually, I want P0 and P2 to be next to each other. So so maybe we want to leave P2 here. But okay, I think that's the reason of confusion. So yeah, okay, so that will be P0 and that will be P1. Right? So we just swap these two, and now we can do it. Of course, it cost us. We had to insert a swap gate. Now, that was trivial, but imagine that we have other gates here. So it's a question of what is the best strategy, and you can think about this strategy to formalize that as an optimization problem. Imagine that you have this quantity, let's call it Lij. This is a variable that is either 0 or 1. It tells you if physical qubit I and logical, it tells you whether in the L layer of the circuit, if we assign the logical qubit I to physical qubit J, then it's 1, otherwise it is 0, right? So you have these binary variables, and now they have a lot of constraints. You want that in each layer, any 2 qubits that are connected, this is going to be 1, because that means that you can actually act on that, because you want them to be next to each other. And of course, you have a bunch of constraints. So what you want to do, you want now to find some strategy when you insert swaps in such a way that, first of all, you have all these constraints satisfied. In each layer, the logical operations always occur between nearby qubits, right? Because otherwise you cannot perform them. But you also want to do it with minimal insertion of swaps. And that's not the only thing. You also want the depth to be minimal, because maybe you can insert swap in a very, very efficient way, but it will be very, very sequential. So your circuit is going to be very long. Maybe you can do it in a very packed way when you insert them in a very parallel way, but then the number of swaps will be overwhelmed. So you need to decide what are the things that what are the trade-offs, and try to solve this problem. It's a satisfaction problem. It's a very hard problem. It's a SAT problem. In general, it's an NP-hard problem. So if I give you a large circuit and I ask you and I give you some device topology, and I ask you, what is the optimal swap strategy, and optimal with respect to whatever we define as optimal, that's a hard problem. We are not going to solve it exactly. There are great heuristics. For small problems, maybe you can solve that exactly, but for big problems, not. And the main question is now, how do you choose your heuristics, and how these different heuristics are going to perform? Once you do that, and your gate and your circuit is valid, in the sense that you only have operations between qubits that at this specific time slice are next to each other, then you'll just use the synthesis that I told you. Now the synthesis is also going to include the swap, because maybe now you had an operation, but now you also added a swap after that. But this is still a 2-qubit operation, and any 2-qubit operation can be written with up to 3 CNOTs, for example, and that's no matter what was the original operation followed by swap. So you make sure that eventually everything is compiled with your native gates, and it's valid. You can execute it on the device. And the last thing that I want to show you is that it matters. So, okay, this is another component, actually, so maybe I'll just mention that. We also need to remember that not all operations are the same. There are some gates that are better than others. If you look at like IBM or IonQ, gate errors are not flat. They're not 4 nines for all single qubit gates, 3 nines for all 2-qubit gates. They're very different. So that's another component that you can add. Maybe you can bias to have more gates on good edges and less gates on bad edges. And in general, it's quite hard because you have a lot of errors and terms that can happen. And this is typically known as the layout selection problem. Now, the layout selection problem can, in general, be solved as part of the routing problem, but since that's so hard, sometimes these days it is separated. So you first get a circuit, you have some logical connectivity, but then there is reality. Your device connectivity is a bit different, so you do this routing and tricks, and eventually you get a circuit that's completely compatible with the operations that you have. But let's say this is eventually the circuit that you have, the connectivity of the circuit. But now if you go to the device, you can see that you can embed this structure in many different ways, right? And so which one is the best? I can say, who cares? I'll just choose one of them and run. But actually, you'll see that the performance can be very, very, this is a very simple example, right? This is just a 16-qubit device. Now, you do typically have some backend data. You know what are the gate errors, you know readout errors. Maybe you can do some characterization to account for crosstalk and so on. And now you can ask, which one of these layouts is going to be the best? Given that I already routed, I have my circuit. That's now non-negotiable. I just want to find the best layout that can account for this circuit. And this is actually a very hard problem. And one of the papers that I'll add to the list is a paper that we wrote that we use algorithms which are a bit like the ranking algorithms when you search something on Google. So in this case, you get as an input the graph of your device, the graph of your compiled circuit, bunch of backend information. Of course, the simple way is just to do simple fidelity multiplication, but this is typically not good enough. And then what you want to rank all the possible different layouts, and eventually you're going to choose one and run your circuit. You're not going to run your circuit on all of these. So this was just a minor. So let me just kind of summarize that. So eventually what you'll have typically an algorithm. You'll need to, first of all, find a way to create a circuit, kind of the assembly level of that. Then you'll typically do some consolidation to some blocks. You'll do routing. You'll do some synthesis. The synthesis actually can be even larger qubits, no matter how many qubits of consolidation. And then eventually you'll just put the pulse level definitions into your gates, and you'll have an executable that you can run on the device. And all I want to show you is that, and I intentionally removed here the legend. You know, this is not a commercial talk. So there are many different compilers out there that you can try them. And you can try them, actually. There's now IBM released this benchmarking suite with thousands of algorithms. Here we just do it on Grover quantum Fourier transform. And you can compare a few things. You can compare compilation time to see how realistic it is, but you also compare how many 2-qubit gates you have and what is the duration of the circuit or how many layers you can have. And the only thing that I want you to take from that, no matter what the numbers are, is that it can be huge. A good compilation and bad compilation can make the difference between having a few thousands of gates to tens of thousands of gates. A good compilation can take a few seconds versus a bad compilation that can take hours. So choosing a compiler and thinking about compiler also when we move to a logical level is a part that we cannot ignore. It can and will be the part that will differentiate between possible to run and impossible to run. So just something to take into account. And the next part that I wanted to talk about is utility, but we won't have time, so maybe in another time we'll talk about applications and utility. So yeah, thank you.